Well, thank you very much for that kind introduction. And it's a real honor to share the Nobelprize in Physics and to speak with you today. My title for this lecture is Turning Potential into Realities and the Invention of the Integrated Circuit. The field of electronics had strong potential when the integrated circuit was invented in 1958. The reality of what people have done with integrated circuits has gone far beyond what anyone, including myself, imagined possible at the time. Charles Towne won the Nobel for his work with laser technology, and he summed up how I feel. Towne said, "It's like the beaver told the rabbit as they stared at the Hoover Dam. No, I didn't build it myself, but it's based on an idea of mine." At its most basic level, the integrated circuit manipulates the characteristics of electricity. In fact, the entire field of electronics is about manipulating the flow of electrons. In other words, making electricity perform advanced kinds of work. A long line of people have been involved in harnessing electricity, from William Gilbert, who first used the word electricity 400 years ago, to Thomas Edison, who built one of the first practical electrical generators in the 1880s. The invention of the vacuum tube launched the electronics industry. Sometimes called electronic tubes, these devices controlled the flow of electrons in a vacuum. They were initially used to amplify signals for radio and other audio devices. This allowed broadcast radio to reach the masses in the 1920s. Vacuum tubes spread steadily into other devices, and the first tube was used as a switch in calculating machines in 1939. By the end of World War II, it was obvious that the cost, bulk, and reliability of vacuum tubes would limit commercial and military electronic systems. A naval destroyer built in 1937 had about 60 vacuum tubes on board. Even the B-29, the most complex equipment used in the war, had only around 300 vacuum tubes. Most of these were single-function tubes, and integration was a low priority at that point. However, electronic systems rapidly grew more complex. The post-war destroyers of 1952 had more than 3,200 vacuum tubes. And of course, the ENIAC computer of 1956 was a vacuum tube monster. It was the world's fastest computer for years, but it contained more than 17,000 vacuum tubes, weighed 60,000 pounds, occupied 16,000 cubic feet, and consumed 174 kilowatts of electricity. Vacuum tubes clearly could not support any significant evolution of computers. People were able to design and visualize systems that, if realized with the prevailing technology, would be too big, too heavy, consume too much power, and simply get too hot to work. And because these components would have to be assembled from tens or hundred thousands of individual parts, they would have been unreliable and unaffordable. By the mid-1950s, these problems were visible to many in the industry, and researchers began seeking a solution. Military applications have always played a major role in the development of electronics. I think the Nobel Peace Prize is important because it honors people who work to bring peace. And peace means that we can use electronics to benefit mankind rather than to wage war. But having said that, the early proponents of miniaturized electronic systems were the U.S. military and space agencies. Most of the approaches tended to make individual components smaller, and so collectively they were called miniaturization programs. Each had a common objective to build complete electronic circuits. T.R. Reid has pointed out that building a circuit is like building a sentence. There are certain standard components, nouns, verbs, and adjectives in a sentence, and resistors, capacitors, transistors, and diodes in a circuit. Each has its own function, and by connecting the components in different ways, you can get different sentences or circuits that perform in different ways. Over the years, each component had been developed with a specialized set of manufacturing processes. The huge step forward came in 1956 when Bell Labs unveiled the transistor. And by creating solid-state components, the race for miniaturized electronic circuits intensified. Transistors rely on the nearly free travel of electrons through crystalline solids known as semiconductors. Semiconductors, such as silicon or germanium, have electrical properties that are midway between that of conductors and insulators. And not surprisingly, that's why they're called semiconductors. We can change the electrical characteristics of semiconductors through a process known as doping, which carefully adds impurities to predetermined areas. Starting with pure silicon, one dopant will add electrons to a particular area. A different dopant will take electrons away to create holes in the area. In either case, we increase the conductivity of the basic material. Semiconductor material that conducts by free electrons is known as N-type. And so, excuse me. Semiconductors that conduct through electron deficiencies are called P-type. At its simplest level, a transistor is a sandwich of these materials, and the components are frequently encased in a ceramic or plastic package. As with most technologies, the techniques for making transistors have made steady progress. The first transistors were known as point contact. They were very primitive by subsequent standards, but they did provide the initial vector. Later techniques included the grown junction transistor, pictured here, and which will crop up later in the lecture. In these transistors, a single crystal of germanium was grown and doped at the same time. The crystal was pulled from a melt containing N-type impurities, and then P-type impurities were added to the molten germanium. Later, more N-type was added. This created an N-doped crystal with a thin P layer within it. And the crystal could then be cut into small blocks, and each block formed a single NPN transistor. Subsequent developments included grown diffuse, alloy, surface barrier, and eventually the mesa and planar types. The earliest transistors were made from germanium, but silicon offered some big advantages in terms of higher operating temperatures, breakdown voltage, and power handling capability. The problem was that silicon was more difficult to work with because of its higher melting point. Shortly before I joined Texas Instruments, that company had solved the puzzle, making silicon transistors commercially available in the mid-1950s. But I'm getting a bit ahead of my story. In 1947, I graduated from the University of Illinois with a degree in electrical engineering. That was the year before Bell Labs unveiled the transistor. But it meant that I started my career at a very exciting time. Although my formal training was in electrical power, I had taken some vacuum tube classes. Unfortunately, I'd also studied a bit of engineering physics because I felt it might be more useful than knowing how to connect three-phase transformers. Looking back, I'm glad I took those physics classes. I wanted to work in electronics, in part because of a childhood interest. My dad ran a power company that served a wide area in rural Kansas, and he used amateur radio to keep in contact during emergencies. I found it very interesting. In fact, it was during an ice storm during my teens, when the customers throughout his area lost power, that I first saw how radio, and by extension electronics, could really impact people's lives by keeping them informed and connected and giving them hope. After graduation, I was hired by Central Lab, a Milwaukee-based electronics manufacturer. They made parts for radio, television, and hearing aids. Central Lab was a very fortunate choice for me because they worked with hybrid circuits, and perhaps the first form of miniaturization. They developed what would become known as thick film hybrid circuits, and in this process, silver paint was deposited on a ceramic substrate or base layer to form conductors. Carbon-based ink formed resistors. Small capacitors could be formed within the substrate and larger ones attached. The necessary vacuum tubes could then be attached with sockets or soldered directly into the substrate. Central Lab was ideal for me in another way. The group I worked for was small, and I was able to see the entire process from engineering through sales and production. My initial duties included the design and product engineering work on hearing aid amplifiers and on resistor capacitor networks for television sets. Since it was a new field, making inventions was easy. Almost anything that departed from previous designs was novel and probably could be patented. In this period, I received about a dozen patents, the most notable being a capacitor design using the first reduced tightenate and a technique for automatically adjusting resistors using sandblasting. In 1952, Bell Labs held their first transistor symposium and began licensing transistor technology for a $25,000 fee. At this time, Central Lab became interested in making transistors and acquired a license. I felt that the transistor pointed the way to the future and I wanted a part of it. After home study and some formal training that included Bell Lab symposia, I became the leader of a three-man project to build transistors and incorporate them into Central Lab product. We built a reduction furnace, crystal puller, zone refiner. This was relatively complex at the time, but growing crystals is similar in principle to a crystal growing kit you might buy for a child today. We used our new equipment to make germanium alloy devices and mounted the unprotected transistors in a plastic carrier, which was a novel design. Environmental protection was achieved by using the ceramic substrate as a part of the hermetic seal. By 1957, Central Lab had established a small production facility that sold small quantities of amplifiers for hearing aids and for some other applications. They were even marginally profitable. But it was clear that the major expenses would soon be required, especially for the military market that was becoming a major opportunity. The military required silicon devices, which added significantly to the capital expense. And by 1958, I had decided to leave and began looking for another job. I talked to several companies and found that IBM had already committed to a technology similar to the thick film work I had done at Central Lab. I felt they had made a basic mistake by choosing a substrate that was much too small. Motorola was interested and thought I could work part-time on my own ideas about miniaturization. But Texas Instruments was more enthusiastic than the others in offering a job working in miniaturization full-time. When I started at TI in May of '58, I had no vacation coming that year. So I worked through the period when about 90% of the workforce took what we then called mass vacation. I was left at that time with my thoughts and imagination, and had already reviewed the earlier attempts at miniaturization. The vast majority of existing transistors held no potential for integration because their electrodes were on different surfaces, offering no real possibility of interconnecting them. Not that someone didn't try. In the early 1950s, the Englishman Joff Dummer of the Royal Radar Establishment suggested that all electronics could be made as a single block. He mentioned the use of amplifying layers, resisting layers, and things of that sort. The electrical functions would be connected by directly cutting out the various layers. It was a remarkable statement, but Dummer gave no concrete proposal on how to do it. His components would not have been all semiconductor, as he also proposed to use thin films with it. But in 1956, Dummer gave a small contract to a British maker to build such a device. They were completely unsuccessful, partly because they worked with the grown junction technology and had difficult interconnection problems. While his device failed, Dummer was on target in general. The body resistance of the semiconductor itself and the capacitance of the junctions between positive and negative regions that could be created could be combined with transistors to make a complete circuit out of the same material. My contribution was taking this idea and making it into a practical reality. While my first duties at TI were not precisely defined, I was free to choose an approach in the general area of miniaturization. The company at that time made transistors, resistors, and capacitors. Since the company could make semiconductors cost effectively, I thought it would be worthwhile to try and make everything from semiconductors. This was contrary to most other efforts at the time, which fell into three basic categories. One group felt that the main problem was the assembly of individual parts, and that by making parts all the same size and shape, they could automate the assembly process. A second group thought that thin films were the way to go, a more modern version of the thick film technology used at Central Lab. Both of these approaches would have used conventional transistors and assembled them to the other components. A third group felt that a more radical approach must be taken. They felt that our knowledge of materials was now complete enough so that entirely new structures could be invented to perform circuit functions. A quartz crystal, which performed the functions of an inductor and a capacitor, was a favorite example. It was clear to me that one of the major problems with all of the existing approaches was that they involved different materials and different fabrication processes. And I began to consider an approach that would reduce the number of both. It was obvious that transistors and diodes could be made of semiconductor material. Discrete or standalone resistors and capacitors could also be made of semiconductor material. However, they would be relatively expensive and neither would perform as well as the best ones made with more conventional techniques and material. For example, tantalum nitride was better for resistors, and Teflon made better capacitors. Even so, since all the components could be made with a single kind of material, it was possible to consider making them all within a single piece of material. And by connecting them properly, complete circuits could be formed. On July 24, 1958, I described in my lab notebook what would come to be known as the monolithic idea. It stated that circuit elements such as resistors, capacitors, distributed capacitors, and transistors, if all made of the same material, could be included in a single chip. I quickly sketched a proposed design for a flip-flop using components made all from silicon. Resistors were provided by the bulk resistance of the silicon, and capacitors formed at p-n junction. I showed the design to my direct supervisor, Willis Adcock, upon his return from vacation, and he asked for proof that circuits made entirely of silicon would work. I therefore built up a circuit using discrete or separate silicon elements, starting with packaged grown junction transistors. Formed resistors by cutting small bars of silicon and etching them. Meantime, capacitors were cut from diffused power transistor wafers, which have been metallized on both sides. Once assembled, the circuit was demonstrated to Adcock on August 28, 1958. This is a representation of it. Had I realized that I would have to look at that thing for 42 years, I would have put a little more effort into its appearance. Fortunately, the test proved that all the circuit elements could be built of semiconductor material. But since I had used discrete components, it was not an integrated circuit, and immediately set out to build a truly integrated circuit. At that time, CI was very strong in grown junction device and just begun to work seriously on diffuse structures. One silicon transistor, a power device with an alloyed emitter, was in production. Several small signal germanium devices were also in production. For these, the emitter and base contacts were evaporated through metal masks. Mesas were etched after hand masking with black wax. I obtained several of these wafers already diffused and with contacts in place. And by choosing a circuit, I was able to lay out two structures that would use the existing contacts on the wafer. The first circuit attempted was a phase shift oscillator, with that shown here, which was a favorite demonstration vehicle for linear circuits at the time. Technicians Pat Harbrecht and Tom Jurgen cut the wafers into bars about 0.12 by 0.4 inches. Metal tabs were alloyed to the back of the bar to provide contacts to the bulk resistor. Black wax was applied by hand to mask the mesas, one for the transistor and a larger one for the diffused region, for performing a distributed RC network. On September 12, 1958, the first 3 oscillators of this type was complete. When the power was applied, the first unit oscillated at about 1.3 megahertz. To show that digital circuits could be built, the same techniques were used to build a flip-flop. That unit was completed on September 19th. By early October, we had begun designing a new germanium flip-flop circuit. This unit was the first to be used and built from scratch. It used bulk resistors, junction capacitors, mesa transistors. And the first units were completed early in 1959 and were later used to publicly announce the solid circuit concept in March of '59. Shortly thereafter, Bob Noyce of Fairchild showed the desirability of using a planar process with metal leads over the oxide. And others, such as Westinghouse, began to contribute to the integrated circuit field. Today, it's a little hard to believe, but in 1958, as we began to announce this idea, and Fairchild publicly discussed Noyce's innovations, there was tremendous criticism. At the time, it was not obvious that the monolithic semiconductor approach was going to succeed over the others I had outlined earlier. Gordon Moore, who's here today, Noyce, a few others, and I provided the technical entertainment at professional meetings for the next 5 years as we described and debated the merits of the various miniaturization systems. There are 3 basic objections to the monolithic circuit. The first was a belief that production yields would always be too low to be profitable. At that time, less than 10% of the transistors made actually worked properly. Another group felt that it didn't make very good use of materials since the best resistors and transistors were not made with semiconductors. And the true transistor people did not want to see their elegant devices messed up with all the other stuff on the chip. These arguments were difficult to counter because they were all basically true. And finally, many people working in the larger companies thought that if semiconductors succeeded, all of the world's circuit designers would be out of work. Of course, the employment of circuit designers has actually increased over the years, but they do work differently than in the transistor era. For TI, the turning point came from 2 highly visible military programs in the 1960s, the Apollo moon mission and the Minuteman missile. The adoption of integrated circuit technology by these programs was a strong endorsement. By 1964, a few venturesome companies had begun putting integrated circuits into commercial equipment. To help popularize integrated circuits, I participated in a TI team that developed the first handheld electronic calculator. Digital equipment was a very early user, and by 1960s, most engineers had accepted the fact that integrated circuits were here to stay. As the concept was accepted, hundreds and later thousands of the best engineers in the world began to work on it. My lecture has focused on the environment immediately preceding and following the invention of the circuit. The innovation and development that has followed in the past 40 years has been more remarkable and far more rapid than all of the developments in the prior 400 years after William Gilbert first coined the term electricity. Thanks to work with hundreds and thousands of the world's best engineers, we've not only created new applications for integrated circuits, we've grown much better at making them. New manufacturing processes have been devised, better transistors have been invented, sophisticated techniques for computer-aided design have been developed. And consequently, the progress in the field was rapid. The early simple chips with a dozen components grew to chips with 10,000 components by 1970, and more than 100 million components today. In Tom Reed's terms, these are not sentences, but encyclopedias. The progress has been accompanied by a rapid decrease in the cost of electronic circuitry. In 1958, a single silicon transistor cost about $10. Today, you can buy a chip with more than 100 million transistors for that price. Costs are almost certainly continue declining in the future. The decrease in cost of more than 1 million to 1 has expanded the field of electronics. Today, powerful personal computers sell for less than $1,000, and these are far more capable than the $10 million versions of the 1960s. And while integrated circuits were used for military applications, today far more are used to improve the quality of life for everyone. Automobiles are safer and emit fewer pollutants because of their integrated circuit systems. Radio and TV have become universal, and hundreds of millions of people are united by the networking power of the internet. Wireless communications keep people in contact with information and other people wherever they go on the planet. And I believe that the best is yet to come. Today, about 1,000 electrons are required to turn an individual transistor off or on. By 2010, it's estimated that this will be accomplished with only 100. The 2010 projection assumes that higher dielectric constant materials will be introduced. If they were not, then the continuation of geometric scaling would extrapolate the reduction to a mere 10 electrons by transistor and by 2010, and just 1 electron by 2020. And that, of course, would present a basic physical limitation. Some projected approaches around this obstacle include quantum, cellular automata, molecular switches, things of that sort. When we reach this nanometer length scale, many people think chemically assembled configurations will begin replacing today's pattern and etch structures. I don't really know how that will play out. But I do know that engineers in all corners of the world are continuing to refine integrated circuits, and others are working on what comes next. I know how they feel. In 1958, my goals were simple: to lower the cost, simplify the assembly, and make things smaller and more reliable. And although I do not consider myself responsible for all the activity that has followed, it's been very satisfying to watch the integrated circuit's evolution. I'm pleased to have had even a small part in helping turn the potential of human creativity into practical reality. Thank you.